The universe runs like perfect clockwork, yet its true mechanics remain almost completely hidden from view, behind the silent expansion of galaxies and the stability of atoms themselves. 25 astonishing mechanisms work in concert to hold everything together. By the end of this journey, you will understand the fundamental blueprint of reality itself. We will uncover how empty space bubbles with energy and why distant particles can communicate instantly. What single cosmic secret most challenges your sense of reality? That first unimaginable burst of energy set the entire cosmic stage. In the tiniest fraction of a second, the universe did something that seems to defy its own rules. It expanded faster than the speed of light. This is cosmic inflation, the first and most dramatic of the hidden mechanisms. The entire cosmos we can observe today was once smaller than a single proton, and then, in a flash, it ballooned to a size larger than our entire visible universe. This was not an explosion into space, but a rapid stretching of space itself. Think of a tiny, crumpled piece of paper instantly smoothing out into a vast, flat sheet. That is what inflation did to the infant cosmos, ironing out any wrinkles and making it remarkably smooth and uniform in every direction we look. Physicist Alan Guth first proposed this idea to solve a profound mystery. Why does the distant universe look so similar in all directions? The heat left over from the Big Bang is almost exactly the same temperature everywhere, yet there hadn't been enough time for these far-flung regions to communicate and even out their energy. Inflation solves this by stating they were once intimately connected before that violent stretch pulled them apart. But this mechanism did more than just smooth everything out. Within that seething quantum foam of the earliest moments, tiny random fluctuations were happening. As space inflated at a phenomenal rate, it stretched these subatomic ripples to astronomical sizes. These minute imperfections became the cosmic blueprints for everything, the gravitational seeds for all the galaxies, stars, and eventually, us. Without that initial burst of inflation, the universe would likely be a chaotic, lumpy mess, or perhaps it would have collapsed back on itself almost immediately. The breathtaking large-scale structure of the cosmos, with its great walls of galaxies and vast empty voids, all trace their origin back to those quantum whispers magnified by inflation. It was the ultimate act of cosmic creation, transforming random noise into a structured universe ready for the next hidden forces to emerge. That initial burst of cosmic inflation left behind a universe that was smooth, but not perfectly so. Its legacy was a faint, frozen imprint of quantum ripples. But what is the source of those ripples? To find it, we must peer into the nature of nothingness itself. The empty space between stars and galaxies is not a true void. Instead, envision it as a bubbling cauldron of frantic activity, a sea of virtual particles popping into and out of existence in an endless, dizzying dance. These are quantum fluctuations, temporary changes in energy that defy our common sense. They arise from a fundamental rule of reality, the Heisenberg uncertainty principle, which states that on the tiniest scales there is always a trade-off. We cannot know both the exact energy of a point in space and the exact time that energy exists. This inherent fuzziness means that empty space is never truly empty. It is filled with an energetic froth where particle-antiparticle pairs are constantly borrowing energy from the universe to spontaneously appear, only to annihilate each other and vanish again a moment later. This is not just a theoretical idea. We can observe its effects. Take two tiny, uncharged metal plates and place them incredibly close together in a perfect vacuum. You would expect nothing to happen, yet they are gently pulled toward each other. This is the Casimir effect. In the narrow gap between the plates, only certain wavelengths of those virtual particles can flicker into being, while outside the plates, a wider variety of particles can appear. The greater pressure from the outside pushes the plates together, a direct physical proof that the vacuum of space is alive with transient energy. These microscopic tremors do far more than just push tiny plates. They are the very seeds from which all cosmic structure grew. Those tiny density variations stretched by inflation, the ones that became the blueprints for galaxies, were themselves born from quantum fluctuations. From the microscopic tremors of the quantum foam emerged the gravitational scaffolding for the entire cosmos, but their influence may be even more profound. This seething energy of the vacuum, known as vacuum energy, is a leading candidate for the mysterious force we call dark energy, the very thing causing the universe's expansion to accelerate. Could it be that these tiny, unpredictable ripples in the fabric of nothingness ultimately hold the key to the ultimate fate of everything? But what would be the point of a universe filled with energy and quantum potential if it had no substance? A cosmos of light-speed particles would simply flash through the void without ever clumping together to form atoms, planets, or people. For the universe to build anything at all, it needed a way to give weight to its fundamental building blocks. This brings us to the third hidden mechanism, an invisible field that acts like a cosmic molasses, slowing some particles down and granting them the gift of mass. This is the Higgs field, an energy field that permeates every corner of the universe, from the vastest void between galaxies to the space between the atoms in your own body. Unlike a magnetic field you can feel with a compass, the Higgs field is always on, a permanent and essential feature of reality. Its existence was a monumental prediction by physicists Peter Higgs and Francois Inglet, and its confirmation required one of the most ambitious experiments in human history. Deep underground, spanning the border between Switzerland and France, the Large Hadron Collider smashed protons together at nearly the speed of light. In the debris of these collisions, scientists hunted for a telltale sign, a tiny ripple in the Higgs field itself known as the Higgs boson. Its discovery in 2012 was a triumph, confirming that this cosmic molasses was not just a theory but a real, physical part of our world. So how does it work? Imagine a crowded room where a famous person is trying to walk through. They interact strongly with the crowd, people cluster around them, slowing their progress and giving them effective mass. An unknown person, however, slips through the crowd with ease, interacting very little and remaining nearly massless. In this analogy, the crowd is the Higgs field. Particles like electrons and quarks interact with this field, and that interaction is what we experience as mass. A photon, the particle of light, does not interact with the Higgs field at all, which is why it zips through the universe at the ultimate speed limit. Without this fundamental mechanism, there would be no stars, no planets, no chemistry as we know it. Electrons would not orbit atomic nuclei, and the universe would be a featureless soup of massless particles. This invisible field does more than just give particles weight. It sets the stage for the next great cosmic force to take hold, the force that sculpts the large-scale structure of the cosmos from the raw material of mass. Mass is the anchor that holds the universe together, but what happens when that anchor is set into violent motion? The very fabric of reality begins to ripple. Spacetime is not a rigid stage, it is a dynamic, flexible fabric that can stretch, warp, and even wave. When truly massive objects accelerate, they do not just move through this fabric, they shake it. These shakes are gravitational waves, distortions that travel outward at the speed of light, carrying the news of cosmic catastrophe across the universe. Albert Einstein predicted their existence a century ago as a consequence of his general theory of relativity, but he thought they would be far too faint for us to ever detect. For decades, they remained a beautiful but unproven mathematical idea. The challenge was immense. How do you measure a ripple in spacetime that might change the distance between 2 points by less than the width of a single proton? The answer arrived in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, heard the unmistakable chirp of 2 black holes colliding over 1 billion light-years away. The signal was a perfect match to Einstein's predictions, a tiny, fleeting wobble in the laser beams of the detectors that confirmed we could now listen to the universe in an entirely new way. The event was unimaginably powerful. For a brief moment, the merging black holes radiated more energy in gravitational waves than all the stars in the observable universe combined. This was not a gentle wave, it was a tsunami in the structure of spacetime itself. So how do these cosmic ripples actually help us understand these violent events? They carry a pure, unaltered story. Light can be blocked, absorbed, or scattered by cosmic dust, but gravitational waves pass through matter almost completely unaffected. They bring us a direct message from the heart of the darkness, from events that are often completely invisible to our telescopes. We are no longer just stargazers, we have become universe listeners, tuning into the vibrations of colliding neutron stars, the final orbits of doomed black holes, and the echoes of the universe's birth. These spacetime wrinkles are a hidden sense, allowing us to perceive the most dramatic and energetic moments in the cosmos, moments that were once forever beyond our reach. These silent gravitational tsunamis ripple through a cosmos already woven with another, deeper kind of mystery. Galaxies spin so fast that they should tear themselves apart, flinging their stars into the endless dark. Yet they do not. They hold together as if wrapped in invisible, unbreakable cocoons. This is the fifth hidden mechanism, the ghostly presence of dark matter. Its existence is not just a theory, it is a mathematical and observational necessity. In the 1970s, astronomer Vera Rubin made a startling discovery while studying the rotation of spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy should move much more slowly than those near the bright center, just as Pluto orbits our Sun far more sluggishly than Mercury. But Rubin's data revealed something entirely different. The stars at the edge of a galaxy were whipping around just as fast as those near the middle. It was as if every single star was feeling the gravitational pull of something far heavier than all the visible stars, gas, and dust combined. The only possible explanation was a vast, invisible halo of matter surrounding each galaxy, a halo with immense mass that holds the entire structure together with its gravitational grip. This dark matter outweighs all the ordinary matter we can see by a ratio of about 5:1. Think of a tiny, glowing city at night, its lights tracing out the familiar spiral shape. Now imagine that this city is actually built upon the slopes of a colossal, invisible mountain, a mountain so huge that the city itself is just a glittering speck on its peak. That mountain is the dark matter halo, the true form of the galaxy, its gravitational anchor. This hidden architecture does far more than just bind individual galaxies. These dark matter halos form a cosmic skeleton, a scaffolding upon which the entire visible universe is built. In the early universe, the gravitational pull of these invisible clumps acted as seeds, gathering clouds of hydrogen gas until they were dense enough to ignite into the first stars and galaxies. Without this dark framework, the universe would lack its grand design, its great walls and filaments of galaxies. We still do not know what this matter is made of. It does not emit, absorb, or reflect light. It only interacts through gravity. It is the universe's most dominant architect, yet it remains utterly invisible to our eyes. What profound secrets of cosmic birth and structure are locked within these dark envelopes? Their immense gravitational pull sculpted the universe, yet it is another, even more mysterious force that is now tearing it apart. Dark matter sculpts the cosmos with its immense gravitational pull, but its work is being undone by something even more enigmatic. The universe is not just expanding, it is accelerating, flying apart at a rate that grows faster with every passing moment. This is the sixth hidden mechanism, the repulsive force of dark energy. For most of the 20th century, scientists believed the cosmic expansion was gradually slowing down, as the collective gravity of all matter acted like a brake on the universe. That assumption was shattered in the late 1990s. Two independent teams of astronomers, one led by Saul Perlmutter and another by Adam Rees, were studying distant stellar explosions called Type 1, a supernova. These supernovae act as cosmic lighthouses, their known brightness allowing us to measure their distance with incredible accuracy. Both teams made the same startling discovery. These supernovae were much fainter and therefore much farther away than they should have been if the universe's expansion was slowing. The only possible explanation was that the expansion of the universe was not slowing at all, it was speeding up. This discovery earned them the Nobel Prize and turned our understanding of cosmic destiny upside down. What could possibly be pushing the galaxies apart with such overwhelming force? The leading candidate is dark energy, a mysterious form of energy inherent to the fabric of space itself. Think of empty space not as a true void, but as a substance that contains a latent, repulsive energy. As the universe expands, more space is created, and with it, more of this repulsive energy. It acts as a sort of anti-gravity, a persistent push that counteracts the inward pull of gravity on the largest scales. This idea was actually hidden in Einstein's own equations for general relativity a century ago, a term he called the cosmological constant, which he later discarded as his greatest blunder. It turns out his mathematics may have been right all along. Dark energy is now calculated to make up about 68% of the total energy density of the universe, completely dominating its composition and its ultimate fate. This leads to a profound and unsettling question: what happens next? If dark energy continues to dominate, its repulsive force will grow stronger as the universe expands. Distant galaxies will eventually be pushed away so fast that their light can no longer reach us. The cosmic horizon will shrink, and the universe will become a much lonelier, colder, and darker place. This mysterious energy holds the key to the final chapter of the cosmos, a force of repulsion that stands in stark contrast to the next great force, the one that builds and binds on the smallest of scales. Dark energy pushes the cosmos apart on the grandest scale, but at the very smallest scales, an even stranger kind of connection defies the very idea of separation. Two particles can be born together and then sent to opposite ends of the galaxy, and yet they remain mysteriously and instantly linked. This is quantum entanglement, the universe's most intimate conversation. When two particles become entangled, they lose their individual identities, sharing a single, unified quantum state. Measuring one particle, say, finding its spin pointing up, will instantaneously force its distant partner to have the opposite spin pointing down. This connection happens immediately, seeming to bypass the cosmic speed limit of light. Albert Einstein was deeply troubled by this, famously calling it spooky action at a distance. He believed it pointed to a flaw in quantum theory, suggesting there must be some hidden, slower-moving variables we could not see. Yet, decades of meticulous experiments have proven Einstein wrong. This spooky action is real. Scientists have sent entangled photons through fiber optic cables across cities, and even from satellites in space to ground stations, and every time, the measurement of one immediately dictates the state of the other, no matter the distance. This is not science fiction, it is a fundamental mechanism woven into reality. So what does this mean for our understanding of the universe? It suggests that the fabric of spacetime, with its strict rules about locality and distance, might be a kind of surface-level illusion. Beneath it, reality could be profoundly interconnected in ways we are only beginning to grasp. This deep connectivity is not just a philosophical curiosity. It is the foundation for emerging technologies like quantum computing and unbreakable quantum encryption. An entangled particle pair acts as a perfect key because any attempt to eavesdrop on their communication would immediately break their delicate link, alerting the users. But the true mystery lies deeper still. How can the universe allow for this instantaneous link? It does not transmit information in the traditional sense. You cannot send a message faster than light using entanglement alone. Instead, it reveals a cosmos where separate objects may not be truly separate at all, but parts of a single, entangled whole. This quantum thread, connecting the farthest reaches of space, hints that the universe operates not as a collection of isolated points, but as an intricately woven network. And within that network, other, more familiar forces are constantly at work, dictating the rules of interaction for every single particle that exists. Quantum entanglement reveals a universe of deep connection, yet for that connection to build anything lasting, a far more powerful and local bond is required. Deep within the heart of every atom, a silent war rages. Positively charged protons are packed unimaginably close together, and their identical charges scream with electromagnetic repulsion, pushing them apart with enough force to tear the nucleus to shreds. Yet they hold fast. They are bound by the strongest glue in the universe, the strong nuclear force. This is the fundamental interaction that does two incredible jobs. First, it acts as an unbreakable strap, holding the fundamental quarks themselves together to form protons and neutrons. Second, its residual effect, spilling outside those particles, creates a powerful attractive force that binds the entire nucleus together against the proton's relentless push to escape. Without this force, the universe would be a soup of lonely, repelling particles, unable to form the complex atoms that are the building blocks of everything we know. The Japanese physicist Hideki Yukawa first theorized this force, proposing a particle called the pion as its carrier. While we now know that the true workhorses are particles called gluons, Yukawa's insight was profound. He correctly identified a powerful, short-range bond operating on a scale of mere femtometers, a millionth of a billionth of a meter. This force is so potent that it is about 100 times stronger than the electromagnetic force that tries to rip the nucleus apart. But it has a peculiar property. Its strength does not diminish with distance in the way gravity or electromagnetism does. Instead, if you try to pull two quarks apart, the energy you put in creates new quarks, locking them back together in a phenomenon called confinement. You can never have a single, free quark. They are forever bound into families. This is the microscopic binding that enables existence itself. It forges the stable atomic cores that allow electrons to orbit and chemistry to happen. It is the force that powers the sun, where the fusion of hydrogen into helium relies on nuclei overcoming their electromagnetic hatred to get close enough for the strong force to snap shut and bind them. From the stability of the air you breathe to the energy of every star in the sky, it all traces back to this invisible, immensely powerful glue holding reality together at its core. Yet for all its power, this force operates in an incredibly delicate balance. one that gives way to a more subtle and precise interaction. The strong nuclear force forges atomic hearts, but it is a far more versatile and far-reaching power that gives those atoms their personality. An invisible web of electric and magnetic fields orchestrates every facet of our reality, from the stability of an atom to the very light that allows us to see. This is the electromagnetic force, the universe's master sculptor of matter and energy. It governs every interaction between charged particles, the push and pull that dictates how atoms link into molecules, how chemicals react, and how life itself functions. The story of our understanding is a tale of unification. For centuries, electricity and magnetism were seen as separate phenomena. Then, in the 1860s, the Scottish physicist James Clerk Maxwell unveiled a set of 4 elegant equations that wove them together into a single, fundamental force. He revealed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This self-sustaining dance is what produces light itself, an electromagnetic wave traveling through the void. Maxwell's work was a monumental leap, but the quantum revolution took it even deeper. Physicists like Richard Feynman developed quantum electrodynamics, a theory that describes with breathtaking precision how charged particles interact by tossing tiny packets of energy back and forth. These packets are photons, the massless particles of light that act as the force carriers for electromagnetism. Every time 2 electrons repel each other, they are doing so by exchanging a flurry of these virtual photons. This force is incredibly powerful and has an infinite range, though its effects are often neutralized in large objects where positive and negative charges balance out. Its influence is absolute. The electromagnetic force determines the entire structure of the atom, dictating how electrons orbit the nucleus and setting the rules for every single chemical bond. The heat from a fire, the energy from the sun, the signal traveling along a neuron in your brain, all of these are electromagnetic phenomena. What would the universe be without this force? Atoms would simply fly apart, light would not exist, and the cosmos would be a dark, lifeless, and structureless expanse. This fundamental interaction not only builds the world we see, it also sets the stage for the grand cosmic cycles, the great recycling processes that breathe life and death into the stars. That same dark matter scaffolding gives the cosmos its most breathtaking visible feature, a sprawling, luminous web. Across unimaginable distances, galaxies are not scattered randomly, they are strung along vast, thread-like structures called cosmic filaments. These are the largest arrangements of matter in the entire universe, immense rivers of dark matter and hot gas that can stretch for hundreds of millions of light years. They form a cosmic skeleton with dense clusters of thousands of galaxies gathering at the intersections like glittering metropolises. For a long time, this was just a theoretical prediction, born from supercomputer simulations like the famous Millennium Run. These digital universes, governed by the laws of gravity and dark matter, consistently evolved to show this intricate, web-like pattern. Then, astronomers began to map the real universe in 3 dimensions, and the simulations came to life. The observations matched the predictions with stunning accuracy, confirming that we live within a cosmic web of staggering scale and order. But what exactly flows within these cosmic threads? Most of the universe's normal matter, the atoms that make up stars and planets, exists here not as galaxies, but as a searingly hot, diffuse gas. This intergalactic plasma is so hot it glows in X-rays, a faint, omnipresent fog that fills the spaces between the galaxies. It is within these filaments that the fate of galaxies is often decided. The intersections where filaments cross are the universe's ultimate construction zones. Here, the gravitational pull is strongest, funneling immense amounts of gas into the waiting embrace of dark matter halos. This is where galaxies are born and where they grow, fed by these rivers of primordial fuel. The very shape of this cosmic architecture guides a galaxy's entire life cycle, determining whether it becomes a quiet spiral or a violent elliptical. This grand design, from the quantum ripples of the beginning to the largest structures imaginable, reveals a universe of profound connection. But how does something so vast and ordered emerge from the chaotic, probabilistic rules that govern the world of the very small? The same invisible energy that pushes tiny metal plates together also stretches the cosmos itself. This is the quantum vacuum energy, a fundamental hum of existence that permeates the complete emptiness of space. Think of the void not as a true nothing, but as a field of unimaginably low energy, the absolute baseline of reality. It is the lowest possible energy state a quantum field can have, but it is not zero. This is not just a philosophical idea, it has real, measurable consequences. We have already seen its handiwork in the Casimir effect, where the pressure of virtual particles pushes plates together. But there is another crucial piece of evidence, the Lamb shift. Physicist Willis Lamb discovered that the energy levels of the electron in a hydrogen atom are subtly shifted from their predicted values. This tiny, precise difference is caused by the electron constantly interacting with the quantum vacuum, jostled by the endless dance of virtual particles around it. This confirmed that the vacuum is not passive. It is an active participant in the behavior of every single particle. This leads to one of the most profound puzzles in all of physics. When we try to calculate the energy density of this quantum vacuum using our best theories, the number we get is absurdly, catastrophically large. It should be 1 followed by 120 zeros stronger than the energy we actually observe driving the acceleration of the universe, the dark energy. This staggering mismatch between prediction and reality is known as the cosmological constant problem, and it represents a fundamental crisis in our understanding. How can the calculated energy of nothing be so vastly different from the energy we see shaping the cosmos? Some theorists suggest a miraculous cancellation, where positive and negative contributions from different quantum fields almost perfectly balance out, leaving behind only the tiny residue we call dark energy. Others propose that we are fundamentally misunderstanding the nature of the vacuum on cosmic scales. This omnipresent energy may have been the engine that powered the universe's initial exponential growth during inflation, and it may be the very force that will determine its final fate, whether it ends in a freeze or a tear. The quantum vacuum energy sits at the precipice of our knowledge, a silent, pervasive influence that challenges us to find the missing link, the deep principle that can finally unite the quantum world with the force of gravity. Yet the profound interconnectedness of the quantum world hints at a deeper, more elegant structure underlying all of reality. Supersymmetry proposes that every fundamental particle we know has a hidden, super-heavy twin. For every matter particle like an electron, a quark, there should be a force-carrying partner. For every force particle like a photon or a gluon, there should be a matter partner. This is not just a doubling of the cosmic cast, it is a profound unification. It suggests that the two great families of particles, the fermions that build matter and the bosons that carry forces, are not separate clans at all, but two faces of a single, more symmetrical reality. The theoretical groundwork for this idea was laid by physicists like Julius Wess and Bruno Zumino, who revealed the stunning mathematical beauty of a world where this symmetry holds. This framework solves some of the most nagging problems in physics. Take the Higgs boson. In our standard model, quantum fluctuations should drive the mass of the Higgs particle to an astronomically high value, making it impossibly heavy. But in a supersymmetric universe, the contributions from regular particles and their superpartners would perfectly cancel each other out, naturally stabilizing the Higgs mass to the value we actually observe. It is a cosmic balancing act of breathtaking precision. Supersymmetry also offers a perfect candidate for dark matter. The lightest of these superpartners would be stable, electrically neutral, and would only interact weakly with ordinary matter, exactly matching the profile of the invisible matter that holds galaxies together. Furthermore, it suggests that the fundamental forces of nature, which now seem so distinct, were truly unified into a single, primordial force at the incredibly high energies of the Big Bang. Despite its elegance, we have not yet found direct proof. The Large Hadron Collider has searched for these superpartners, but so far they have remained hidden, suggesting they are far heavier than we had hoped. Their absence tells us that if supersymmetry is real, it is a broken symmetry, a perfect law that was only fully manifest in the universe's first searing moments. What hidden particles might be waiting in the next tier of energy, just beyond our current reach? The search for this symmetry is a search for the universe's hidden mathematical heart, a quest that leads us directly to the unbreakable rules that govern every single interaction, the great conservation laws. These unwavering rules of conservation are the universe's ultimate set of instructions, a strict code that reality cannot break. Visualize the cosmos as a master accountant, constantly balancing its books. Through every star's fiery birth and every particle's collision, certain totals never change. The universe can transform energy from one type to another, shift momentum between objects, and redistribute charge, but it can never create or destroy these fundamental quantities. This is the hidden mechanism of conservation laws, and they impose a deep, predictable order on every process, from the quantum realm to the dance of galaxies. Their power comes from a source of breathtaking elegance, a connection between the tangible laws we observe and the abstract beauty of symmetry. This link was forged by the mathematician Emmy Noether in the early 20th century. Her revolutionary theorem revealed that every continuous symmetry in nature corresponds to a conserved quantity. It is a concept of profound depth. For instance, the fact that the laws of physics are the same today as they were yesterday, a symmetry in time, leads directly to the conservation of energy. The fact that the laws of physics are the same here as they are in a distant galaxy, a symmetry in space, leads to the conservation of momentum. And the fact that the laws of physics are the same no matter which direction you face, a rotational symmetry, leads to the conservation of angular momentum. These are not separate rules but different facets of a single, deeper truth about the fabric of reality. These laws are the strict gatekeepers of the possible. In a particle collision, energy and momentum must add up to the same total before and after the event. This constraint dictates what new particles can be created and how they will fly apart. Electric charge must be meticulously preserved. You cannot simply create a negatively charged electron without also creating a positively charged positron. This is why matter is always created in particle-antiparticle pairs. How do these rigid rules enable the complexity we see around us? They provide the stable foundation upon which everything is built. The conservation of angular momentum is why a spinning ice skater pulls their arms in to spin faster, and it is also why the planets continue their orderly orbits around the Sun. Their angular momentum, a constant, unchanging value that maintains the solar system's stability. Without the conservation of energy, stars could not steadily fuse hydrogen for billions of years, releasing precisely the energy bound within their atomic nuclei. These laws are the invisible scaffolding that prevents the universe from descending into chaos, ensuring that for every action, there is a predictable and constrained reaction. They are the reason reality is comprehensible and reliable, the silent, unbreakable rules that give rise to the stability of matter itself. Those silent, unbreakable rules of conservation grant the universe its stability, but they do not explain its stunning diversity. For that, we must descend into the heart of the atom itself, where a different, more stubborn law takes over. The electrons orbiting an atomic nucleus are not free to crowd together. They are cosmic individualists, each one demanding its own unique quantum address. This is the Pauli Exclusion Principle, a fundamental decree that no two identical fermions, the particles that make up matter, can occupy the exact same quantum state at the same time. Austrian physicist Wolfgang Pauli introduced this rule in 1925 to explain the structure of atoms, and it solved a profound mystery. If electrons could all sink down to the lowest energy level, every atom in the universe would look nearly identical, and chemistry as we know it would simply not exist. The principle acts as a form of quantum social distancing. Think of a multi-story car park where every single parking space is reserved for one specific type of car. An electron with a certain spin can only park in its designated spot. Once a spot is taken, no other electron of that same type is allowed in. This forces electrons to occupy higher and higher energy levels or floors as you add more of them to an atom. This simple, unyielding rule is the entire reason for the periodic table of elements. The different chemical properties of hydrogen, carbon, oxygen, and gold are not due to some fundamental difference in their electrons or protons, but are a direct consequence of how their electrons are arranged in these distinct structured shells, all dictated by Pauli's principle. Without it, all matter would collapse into a dense, featureless mush, but its power extends far beyond the chemistry lab. When a star like our Sun dies, it sheds its outer layers and its core collapses under its own gravity. The collapse is halted not by nuclear fusion, but by electron degeneracy pressure, a direct result of the Pauli exclusion principle. The electrons are squeezed so tightly that they resist further compression simply because there is no more available quantum space for them to occupy. This creates a white dwarf, a stellar cinder about the size of Earth. For more massive stars, the collapse is even more violent, crushing electrons and protons together to form neutrons. Once again, the Pauli principle asserts itself, creating an even more immense neutron degeneracy pressure that can halt the collapse, forming a city-sized neutron star so dense that a single teaspoon of its material would weigh billions of tons. This quantum refusal to be in the same state is what builds the very structure of our world and supports the most exotic objects in the cosmos. It is the fundamental mechanism that prevents the universe from collapsing into uniform dullness, creating instead a rich tapestry of elements and materials. This relentless pressure holding back the crushing weight of gravity hints at the incredible energies involved when these cosmic balances are finally overcome. That quantum pressure holding up entire stars is a testament to the fierce laws governing the small scale, but there is a far older, far colder whisper that tells the story of the largest scale of all. Two astronomers working for Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent, maddening hiss in a massive radio antenna. They scrubbed away pigeon droppings and checked every connection, but the faint, uniform static remained, coming from every direction in the sky with no regard for day or night. They had accidentally stumbled upon the oldest light in the universe, the cosmic microwave background. This is the lingering afterglow of the Big Bang, a fossilized echo from a time when the cosmos was a mere 380,000 years old. Before that moment, the universe was a searing, opaque fog of plasma, too hot for light to travel freely. Electrons and protons were constantly scattering photons, trapping the light in a relentless dance. But as the universe expanded and cooled, electrons and protons finally combined to form the first neutral atoms. In that instant, the fog lifted. The universe became transparent, and that first burst of light, once blazingly hot, was finally set free to travel across the cosmos. Over the ensuing 13.8 billion years, the stretching of space itself has stretched that light, cooling it from thousands of degrees to just 2.7 degrees above absolute zero. It now exists as a faint microwave signal that uniformly bathes the entire universe, a cold relic of a fiery birth. But this radiation is not perfectly smooth. When scientists built satellites like COBE, WMAP, and Planck to map its temperature with exquisite precision, they discovered tiny fluctuations, variations of just a few millionths of a degree. These minute-hot and cold spots are the cosmic blueprints imprinted on the sky. They are the gravitational seeds, the slightly denser regions where dark matter had already begun to clump, that would eventually grow over billions of years into the great cosmic web of galaxies and voids we see today. This ancient snapshot confirms the universe began in a hot, dense state and provides our most powerful evidence for the Big Bang model. It has allowed us to measure the age, composition, and geometry of the cosmos with astonishing accuracy. The precise patterns in this light tell us exactly how much ordinary matter, and dark energy exist. What profound secrets does this ancient light still hold? It is a direct message from the universe's infancy, a picture of the initial conditions that set the stage for every galaxy, star, and planet that would ever form. That ancient light from the cosmic dawn gives us a snapshot of the infant universe, but another, even more subtle fossil is woven into the distribution of the galaxies themselves. Sound waves, massive pressure waves that once rippled through the primordial fireball, left a permanent imprint on the cosmos. These are Baryon acoustic oscillations, a cosmic echo frozen in time. In the first few 100,000 years after the Big Bang, the universe was a seething, hot plasma, a tight coupling of light and matter. In this dense fluid, gravity would try to pull matter inward, creating an overdense region. But the intense radiation pressure would fight back, creating a powerful outward push. This tug of war set up a spherical sound wave, a density wave that raced outward from every initial lump at over half the speed of light. This grand cosmic bell was ringing everywhere at once. Then, the universe cooled just enough for atoms to form. In that moment of decoupling, when the fog lifted and the cosmic microwave background was released, those sound waves were suddenly frozen in their tracks. The matter that was caught at the leading edge of these waves was left stranded in a spherical shell. The result is a subtle but detectable pattern in the way galaxies are spaced across the heavens. If you could map the positions of millions of galaxies, you would find that they are slightly more likely to be separated by a specific distance than any other. That preferred distance is the fossilized size of that sound wave at the moment it was frozen, a cosmic ruler stretching about 500 million light-years. This standard ruler is one of the most powerful tools in modern cosmology. By measuring how this apparent size changes across different cosmic eras, we can trace the history of the universe's expansion with phenomenal precision. Surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument are creating vast three-dimensional maps of the cosmos, and the Baryon acoustic oscillation signal stands out clearly within them. How does this help us understand dark energy? The ruler appears smaller at greater distances than our models predict, confirming that the expansion of space has been accelerating over billions of years, driven by the repulsive push of dark energy. This fossilized sound connects the universe's first moments to its ultimate fate. a permanent rhythm written into the stars that helps us measure the very constants that dictate the laws of physics. These frozen cosmic sound waves reveal a universe governed by precise mathematical rules, but what writes the rules themselves? The universe runs on a set of unchanging numbers, the fundamental constants. These are not physical objects or forces, but pure numerical values that are baked into the very fabric of reality, defining the strength of every interaction and the scale of everything from atoms to galaxies. The speed of light in a vacuum is always exactly 299,792,458 meters per second, a universal speed limit that nothing can exceed. Planck's constant sets the discrete size of the quantum realm, the smallest possible unit of action. The gravitational constant determines the weakness of gravity's pull. These values are not derived from any deeper theory. They are simply the way our universe is built. For decades, physicists like Paul Dirac have been struck by a profound curiosity. Why these numbers? Why not others? The fine structure constant, a pure number near 1/137, governs the strength of the electromagnetic force. Its value controls how tightly electrons bind to atomic nuclei, dictating the entire landscape of chemistry. If it were just a few percent larger or smaller, the nuclear reactions in stars would fail. Carbon, the essential element for life, would never be forged in stellar furnaces. The cosmological constant, which sets the energy of empty space, is equally precise. If it were slightly stronger, the universe would have blown itself apart before the first stars could form. If it were slightly weaker, the cosmos would have collapsed back into a superheated crunch long ago. This apparent fine-tuning is stunning. It seems as if the dials of the universe were set with incredible care to allow for complexity, structure, and ultimately, observers. This leads to the Anthropic Principle, a simple yet powerful idea. The constants must be compatible with our existence because we are here to observe them. In a multiverse of countless universes, each with its own random set of constants, we naturally find ourselves in one of the rare habitable ones. But is this the final answer, or is there a deeper, more fundamental reason for these specific values? These constants are the silent, unwavering foundation for all the periodic processes we see, from the steady pulse of a pulsar to the stable orbit of a planet. They are the ultimate settings on the cosmic control panel, and their precise values are the greatest unsolved puzzle in physics. These unwavering constants set the stage for the universe's most majestic performances, the great cosmic cycles that transform chaos into order and back again. Across the vast expanse of space and time, the universe breathes in a slow, rhythmic dance of creation and destruction. A star is born from the collapse of a cosmic cloud, shines for billions of years by fusing hydrogen into heavier elements, and then dies in a spectacular explosion that scatters those new atoms back into the void. This expelled material, enriched with carbon, oxygen, and iron, eventually coalesces into new clouds, new stars, and new planets. The very atoms that make up your body were forged in the heart of a long-dead star, scattered across the galaxy, and then gathered together to become part of our world. This is the stellar life cycle, a continuous recycling program on a galactic scale that turns the primordial hydrogen and helium from the Big Bang into the diverse elements necessary for planets and life. This rhythm extends to even grander scales. Our Sun, for instance, orbits the center of the Milky Way galaxy once every 230 million years, a single galactic year. On a theoretical level, some models imagine the entire cosmos undergoing an ultimate cycle, a perpetual series of big bangs and big crunches where the universe expands, contracts, and rebirths itself in an endless loop. While our current evidence strongly suggests a perpetual expansion driven by dark energy, the poetic appeal of a cyclic universe remains, hinting at a deeper, perhaps infinite, pattern of renewal. Even the mysterious dark energy could be part of a slow cycle, its strength waxing and waning over trillions of years. From the steady pulse of a pulsar to the majestic, predictable orbits of planets, cyclic behavior is woven into the cosmos at every level. Do these vast, repeating patterns, from the explosive death of a star to the slow spin of a galaxy, reflect a fundamental rhythm inherent to spacetime itself? This grand cosmic choreography governing the very large finds its origins in the precise and probabilistic dances of the quantum world, where the behavior of the smallest particles dictates the fate of the largest structures. The precise cosmic cycles that govern the stars find their origin in a strange kind of magic at the quantum scale. Particles can perform an impossible feat. They can simply vanish on one side of an energy barrier and reappear on the other, as if a ball thrown at a mountain suddenly appeared on the far slope without ever going over the top. This is quantum tunneling, a ghostly mechanism that defies every intuition of classical physics. It arises from the fundamental wave-like nature of all particles. In the quantum realm, a particle is not a tiny speck but a cloud of probability described by its wave function. When this probability wave encounters a barrier, it does not abruptly stop, it exponentially decays inside the barrier. If the barrier is thin enough, there is a real, calculable probability that the wave function, and therefore the particle itself, will be found on the other side. The German physicist Friedrich Hund first uncovered this phenomenon in 1927 while studying how molecules interact, revealing a hidden layer of reality where the impossible becomes routine. This quantum magic is not a theoretical curiosity, it is essential for our very existence. Deep within the core of our sun, protons are repelled by the immense electromagnetic force pushing them apart. Classical physics says they should never get close enough to fuse, yet they do. They achieve fusion by quantum tunneling through that repulsive energy barrier, a process that happens countless times every second to power the star and provide the Earth with light and heat. Without this mechanism, the Sun and all other stars would be dark, cold objects. The same principle enables radioactive decay, where an alpha particle tunnels out of an atomic nucleus, and it is the operational heart of modern electronics like flash memory and tunnel diodes. Its influence even extends into biology, where it drives the efficiency of enzymes and is fundamental to the process of photosynthesis. How does this quantum magic enable processes essential for life? It allows for chemical reactions and energy transfers that would otherwise be far too slow or energetically impossible, weaving this subtle, probabilistic process directly into the fabric of life itself. This ability to bypass barriers hints at a universe where information, the most fundamental currency of reality, can persist in the most extreme environments imaginable. Quantum tunneling allows particles to bypass impossible barriers, but there exists a cosmic vault from which nothing, not even information, is supposed to escape. A black hole presents a profound challenge to our understanding of reality itself. According to Einstein's general relativity, a black hole is defined by its event horizon, a point of no return. Anything that crosses this boundary, whether a spaceship, a planet, or a single particle of light, is lost forever to the outside universe, its information seemingly crushed into a single point of infinite density, the singularity. This description, however, creates a catastrophic conflict with the other pillar of modern physics, quantum mechanics. Quantum theory holds a fundamental law, the principle of unitarity, which states that information can never be truly destroyed. It can be scrambled, transformed, or hidden, but it must be preserved in some form. You cannot burn a book and make its information truly vanish. The arrangement of the ash and smoke still contains a scrambled record of its pages. For decades, physicists assumed that black holes were the one true exception to this rule, a cosmic shredder that permanently erased information. Then Stephen Hawking made a startling calculation. He showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate energy, a faint glow we now call Hawking radiation. This radiation causes the black hole to gradually lose mass and evaporate over astronomical timescales. The paradox emerges with a devastating question: what happens to all the information about the stuff that fell in? Hawking's initial work suggested that the radiation was purely thermal, random and featureless, carrying no information about the black hole's interior. If the black hole evaporates completely, leaving behind only this random heat, then the information about everything it ever consumed is permanently lost, violating the core tenet of quantum mechanics. This is the black hole information paradox, a direct clash between our two most successful descriptions of nature. Resolving this paradox has forced physicists to propose extraordinary ideas. One leading solution is the holographic principle, which suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its event horizon, like a cosmic fingerprint pressed onto a two-dimensional surface. The three-dimensional interior of the black hole is somehow a projection of this two-dimensional information. Another radical idea is the firewall hypothesis, which proposes that the event horizon is not a smooth gateway but a blazing wall of high-energy particles that instantly incinerates anything that touches it, preserving information by never letting it actually enter. Or perhaps black holes do not vanish entirely, leaving behind a tiny, information-packed remnant. Each of these solutions has profound implications. The holographic principle, in particular, suggests that our perception of a three-dimensional universe might be an illusion, a hologram projected from a two-dimensional reality at the cosmic horizon. This paradox is not just a theoretical puzzle, it is a glaring signpost pointing toward the next great unification in physics, a theory of quantum gravity. What does this fundamental conflict reveal about the true nature of spacetime? It hints that space and time themselves may be emergent properties, arising from a deeper layer of interconnected quantum information. This staggering idea forces us to question the very nature of our own reality. The holographic principle proposes that our seemingly three-dimensional universe, with all its depth and volume, might be a magnificent illusion, a projection of information stored on a distant, two-dimensional surface. Think of the experience of watching a high-definition movie on a flat screen. The image has depth and movement, a convincing three-dimensional world, yet you know all that information is encoded on the flat, two-dimensional surface of the screen. The holographic principle suggests our cosmos operates in a similar, though far more profound, way. The entire description of everything within a volume of space, every star, every planet, every one of us, could be entirely encoded on its boundary, like a cosmic fingerprint pressed onto the surface of a sphere. This revolutionary concept was pioneered by physicists Gerard T. Hooft and Leonard Susskind, who were grappling with the deepest puzzles of black holes. They realized that a black hole's entropy, which is a measure of its information content, does not scale with its volume as you might expect. Instead, it is precisely proportional to the surface area of its event horizon. This was a monumental clue. It suggests that the maximum amount of information you can pack into any region of space is not limited by its volume, but by the area of its surface. The universe, it seems, has a fundamental pixelation, a finite information density. if this is true, then our rich, three-dimensional experience is not the fundamental reality. The third dimension, the very feeling of depth and immersion, emerges from the incredibly complex processing of information on that underlying two-dimensional surface. This is not just a philosophical thought experiment. The holographic principle is a cornerstone of serious approaches to quantum gravity, most notably in string theory through the anti-de Sitter/conformal field theory correspondence, which provides a precise mathematical dictionary translating a gravitational theory in a bulk volume to a quantum field theory on its boundary. So, is our reality fundamentally flatter than we perceive? This perspective shifts our view of the cosmos from a place of things to a realm of information, a cosmic computation where space and time themselves are not the stage, but actors emerging from a deeper, more fundamental layer of bits. This informational view of the cosmos leads us to a truly mind-bending question. Could the entire universe be operating like a colossal, unimaginably complex computer? Our very existence as observers forces a profound constraint upon the cosmos. The universe we measure is not a random sample of all possible worlds. It is the only kind we could possibly find ourselves within. This is the Anthropic Principle, the startling idea that the fundamental parameters of reality must be compatible with the presence of conscious life, for the simple reason that we are here to notice them. Physicist Brandon Carter formally introduced this concept in 1973, framing it in two distinct ways. The weak anthropic principle notes that our location in the universe must be compatible with our existence as observers. We could not find ourselves in the empty void between galaxies or in the searing heat of the early cosmos. The strong version makes a bolder claim, suggesting that the universe itself must have properties that allow for the emergence of consciousness at some point in its history. This is not an explanation in itself, but rather a powerful filter for our theories. It helps us understand the staggering fine-tuning of the fundamental constants without needing to invoke a designer. Consider the cosmological constant, the value of dark energy. If it were slightly stronger, the universe would have blown apart before galaxies could form. If it were slightly weaker, it would have collapsed back into a fiery crunch. The force of gravity, the strength of the nuclear forces, the mass of the electron, all seem precisely calibrated to allow for stars, planets, and complex chemistry. The Anthropic Principle suggests a simple yet vast solution. Our universe is just one of countless others in a grand multiverse. In this cosmic landscape, each universe has its own random set of physical laws and constants. We, of course, can only exist in one of the rare, habitable ones where the numbers line up just right. While controversial for some, this framework transforms the question from why is the universe fit for life to what physical mechanism could generate such a vast ensemble of universes. Does our conscious observation somehow reach back and lock in the very laws we see? This observer-centric view hints at a cosmos where life is not a random accident, but an integral part of a deeply interconnected reality. This delicate quantum choreography extends far beyond the confines of a laboratory. Quantum coherence describes a state where particles are not just individuals, but act as a single, unified wave, their phases locked together in a perfect, coordinated dance. It is this synchronized wave-like behavior that allows for the most exotic states of matter we know. In a superconductor, for instance, electrons overcome their natural repulsion to form what are known as Cooper pairs. These pairs, all coherent with one another, can flow through a material without any resistance at all, a collective quantum behavior that enables the powerful magnets in MRI machines and promises lossless power grids. Similarly, in a superfluid, atoms coalesce into a single quantum state, allowing the liquid to flow without any viscosity. It can climb up the walls of its container in a thin film or spin in a vortex that never slows down. These are not just curiosities, they are profound demonstrations of coherence on a macroscopic scale, where the bizarre rules of the quantum world manifest in a form we can see and touch. The challenge, and the reason we do not see this everywhere, is the fragility of this state. Coherence is easily shattered by the slightest interaction with the chaotic outside world, a process called decoherence. A single stray photon or a random vibration can cause this delicate quantum waltz to collapse into a disorganized classical jumble. This is the central obstacle in building a practical quantum computer, a machine that relies on maintaining coherence in its quantum bits or qubits to perform calculations of unimaginable complexity. Yet, what if this fragile coordination is not just a human-made phenomenon? Some physicists speculate that certain forms of dark matter could be coherent on astronomical scales, or that the earliest moments of the universe were governed by coherent phase transitions that shaped the fundamental forces. The idea even stretches into the realm of biology, with theories suggesting that quantum coherence might play a role in the efficient workings of photosynthesis or even the nature of consciousness itself. How does this coordinated quantum behavior, so easily disrupted in our hands, manage to shape phenomena across the cosmos? The answer may lie in the ultimate isolation of the quantum vacuum, a perfect stage set by the universe's own boundary conditions. Our cosmic vision is ultimately bounded by a final, unbreachable wall. The cosmological horizon marks the absolute edge of our observable universe, the maximum distance from which any signal, even light, could have possibly reached us since the dawn of time. This is not a physical barrier floating in space, but a frontier in time itself, a consequence of the universe's finite age and the unwavering speed of light. The most distant light we can see is the cosmic microwave background, emitted when the universe was only 380,000 years old. Because space itself has been stretching for nearly 14 billion years since that light began its journey, the source of that ancient radiation is now an astonishing 46 billion light-years away. We are surrounded by a horizon that defines everything we can ever know. There are different kinds of these cosmic boundaries. The particle horizon encloses all the points we have ever been able to see in the past, while the cosmic event horizon represents the farthest point from which a signal sent today could ever reach us in the future. Due to the accelerating expansion driven by dark energy, galaxies beyond a certain critical distance are already crossing this ultimate threshold. Their light, though still streaming toward us, is fighting a losing battle against the stretching of space. One by one, those distant islands of stars will slow their clocks in our telescopes, redden into invisibility, and finally wink out of existence, their future light forever lost to the ever-growing void between us. This leads to a future of profound isolation. Billions of years from now, our local group of galaxies will have merged into a single, giant galaxy, and every other galaxy cluster will have vanished beyond the cosmological horizon. The sky will go dark for any future astronomers, leaving them with no evidence of a broader cosmos or its explosive beginning. They will inhabit an island universe cut off from the cosmic web, with no way of knowing what came before. This horizon is not just a limit on what we see, but a fundamental limit on knowledge itself. It dictates the total amount of information we can ever gather about the cosmos. What lies beyond this ultimate veil? Is it an infinite fractal repetition of universes like our own, or something so alien our physics cannot yet describe it? The very existence of this horizon forces us to confront the limits of our scientific reach and compels us toward the final, deepest of the hidden mechanisms, the one that seeks to unify all of reality into a single, elegant equation. That ultimate unification is the final and most ambitious quest in all of science. A single, elegant equation that describes everything, from the frantic dance of a quark to the majestic whirl of a galaxy, has been called the theory of everything. It is the dream of a single mathematical framework that would finally heal the great rift in physics, seamlessly weaving together the cosmic gravity of Einstein's general relativity with the probabilistic weirdness of quantum mechanics. For decades, these two pillars have stood apart, each magnificently accurate in its own domain, yet fundamentally incompatible when their realms collide, such as at the center of a black hole or the moment of the Big Bang. Albert Einstein himself spent the last 30 years of his life searching for this unified theory, a quest he called his unified field theory, though it ultimately eluded him. Today, that torch is carried by brilliant minds like Edward Witten, who explores the intricate landscapes of string theory, and Carlo Rovelli, who develops the granular structure of loop quantum gravity. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. The different notes these strings play would manifest as different particles and forces, with gravity naturally emerging from the music of the strings. Loop quantum gravity, in contrast, suggests that space and time themselves are not smooth and continuous, but are woven from a fabric of tiny, discrete loops, quantized much like the pixels on a screen. A successful theory of everything would do more than just reconcile two theories. It would explain why the universe has the precise properties it does, why the fundamental constants have the values they do, and perhaps even answer the question of why there is something rather than nothing. It would reveal all particles and all forces as different facets of a single, underlying reality. The challenges, however, are monumental. The mathematics involved is ferociously complex, and experimental verification seems, for now, nearly impossible, as the energies required to probe these scales are far beyond anything we can create. Perhaps the most profound challenge is explaining the emergence of spacetime itself. Does space and time arise from something more fundamental, a deeper network of relationships or quantum information? Could it be that our experience of a continuous, flowing reality is a grand illusion, a shadow of a far stranger truth? This grand quest, the search for a single equation that encapsulates the entire cosmos, represents the pinnacle of human curiosity. It asks if the ultimate blueprint of reality is written in a language we are capable of reading, and whether the final, unifying secret of the universe is one we are destined to understand. Humanity's quest to understand the cosmic clockwork has always been shaped by the metaphors of its time. Ancient cultures looked to the heavens and saw the hands of gods, divine beings who guided the sun across the sky and hurled lightning from the mountains. The stars were not distant furnaces but celestial campfires, and the orderly progression of seasons was a gift from powerful, capricious deities. This mythological framework provided a story, a reason for the universe's apparent order, even if it was not a scientific one. Then, in ancient Greece, a new kind of thinking emerged. Philosophers like Aristotle envisioned a universe of perfect, concentric crystalline spheres, each one carrying a planet or star in an eternal, unchanging dance around the Earth. This was a mechanical model, the first great shift from supernatural will to physical structure, yet it was still rooted in a vision of celestial perfection separate from the flawed, changing world below. The real revolution came with Isaac Newton. After observing an apple fall, he realized the same force that pulled the fruit to the ground also reached across the void to guide the moon in its orbit. This was a monumental leap. Newton's universe was a vast, predictable clock, wound up by a divine creator and set ticking according to immutable mathematical laws. Gravity was the invisible spring that drove the mechanism, and for centuries this clockwork model reigned supreme. It was a framework born from the technology of its age, the intricate gears and pendulums of precise timekeeping devices. The next great metaphor emerged with Albert Einstein, who shattered the very idea of a rigid cosmic clock. His work revealed that space and time were not a static stage but a flexible fabric, warped and curved by mass and energy. The universe was not a clock, but a dynamic, living entity where gravity was not a mysterious force, but the geometry of spacetime itself. This relativistic model reflected a new technological sophistication, one of fields and energies, much like the electromagnetism that was powering the modern world. Today, we often describe the cosmos in terms of quantum computing or cosmic holograms, metaphors drawn from our own digital revolution. Each era's dominant technology provides the language and the conceptual tools to probe deeper. The water clock led to the mechanical clock, which led to the computer simulation. Our frameworks are not just descriptions, they are lenses that focus our curiosity and determine what questions we can even think to ask. So what comes next as we develop artificial intelligence and dive deeper into virtual realities? What new metaphors will we create? Perhaps the next great cosmic mechanism will be discovered by a mind trained to see the universe not as a computer, but as something we cannot yet even name. Our journey through the cosmos reveals a universe held together by a symphony of unseen forces. We have explored 25 remarkable mechanisms, from the quantum tremors that seeded all galaxies to the dark energy now tearing them apart. Each hidden architecture, from the cosmic molasses of the Higgs Field to the spooky connection of entangled particles, shows a reality far more intricate and interconnected than our everyday senses can perceive. Invisible fields and silent forces orchestrate this grand performance, conducting everything from the stability of atoms to the acceleration of the cosmos itself. The true wonder lies in their delicate interdependence. This is a cosmic ballet of breathtaking precision, where altering a single element, just one fundamental constant or one hidden interaction, would cause the entire tapestry of existence to unravel. There would be no stars, no planets, and no one to wonder at the silent majesty of it all. The physicist John Archibald Wheeler captured this beautifully when he said that we live on an island of knowledge surrounded by a sea of ignorance. As our island grows, so too does the shoreline of what we do not know. Every answer births new and deeper questions. I encourage you to carry this curiosity forward. Explore these cosmic mysteries further, perhaps starting with the resources waiting for you in the description below. And I would love to hear from you. Share in the comments which of these hidden mechanisms most captivates your imagination, and tell me why it reshapes your view of the universe.